Alrighty, good morning, ladies and gentlemen. Happy Monday. Welcome back to remote learning. I apologize about the audio quality. The air blower inside of the school is much louder today, so you might hear some background noise. Today, we're going to wrap up our real-world graphing scenario. So this is kind of finishing up our linear relationships. So what I'm going to talk about today are some things that can connect what we've been learning to the real world, which is what it's all about. So to start, I'm going to show you the idea of what's called a scatterplot. And what a scatterplot is oftentimes when we are looking at things in the real world, we want to compare two things. So this might be connected to our pattern number and how many blocks we were counting, but with a real world context. So for example, this person is measuring time versus length. So maybe something is growing, they're growing some vegetables in a garden, they want to see how many hours has to go by for something to grow a certain size. So they've made a bunch of measurements and they've plotted them out. So one of the things about a scatter plot is that you'll end up with a bunch of basically XY coordinates, and we fill them out and basically fill in our graph. Now, one of the things I want you to notice is that they're basically all they've done is taken all the values they have and have filled out this graph. But one of the things you'll notice right away is that this does not make a perfectly straight line. It kind of curves a little bit. But here's the thing. There is a pattern to it. It's not random. For example, a conclusion is as time goes up, length increases. And part about this is that we're never going to be truly 100% accurate to our linear equations. So linear equations kind of fall apart when we think about the real world, and I'll talk about why in a little bit. But one of the things you can notice is that if I get a ruler and draw kind of a line approximating going through, I might do something like this. So this is what's often known as a trend line or a best fit line. There are other ways I can do it. I could have followed the line a little bit more closely. Like I noticed the line sort of goes like this. So I might want to track it like that. But in this case, what I want is that my best fit line or my trend lines are linear. So we're trying to draw a straight line to a relationship. And here is where we get to our first key term. We have talked about trend lines, but this one is correlation. This is what we'll call a predictable pattern between two real-world variables. So in the previous one, our two variables were length and time. So as time increases, so too does the length, and it does so in a predictable pattern. So this means that there is some sort of relationship between these two variables. So for example, this one's talking about birds chirping. So if I was to draw a best fit line here, I notice the number of chirps. As the number of chirps goes up, if I draw kind of a line going through, not my best work. Here, let me erase that and kind of swap it a little bit. I notice that there is a definite line as it goes up. And my y-axis is the temperature. So I can think as temperature goes up, the number of chirps increases. Or vice versa. As I hear more bird chirping, it's probably a higher temperature. Another example, this one's a little bit harder to see, but average daily temperature is on our bottom, and then beach visitors. And if I make a rough line, I can kind of see that there is a trend here. The reason being is that there's nothing here, and there's almost nothing here. So what I have is these two big empty spaces, and I can guess that as temperature goes up, so too do the visitors. So as temp increases, visitors increase as well. Now, one of the things, so far I've drawn all these lines kind of going up and to the right, positive slope. This is what we call a positive correlation, but it doesn't have to be. So for example, I could have a negative correlation. This one just gives me variables, but you can see they've drawn a trend line and that there's some above, some below, but on average, they follow this sort of trend pattern down. Another example I can use is, say, number of missed classes versus an exam score. We see here that on average, when students miss more classes, their scores become lower. And again, there's some above my line, there's some below my line, but on average, they kind of follow this pattern. So one of the things we can talk about, we can have positive correlation, we can have negative correlation, but one of the other things we can talk about is we can also have what's called strong or weak correlation. And this is how well our trend line matches our data. So how strong our correlation is related to how closely connected these two variables are. To show you what this kind of looks like, don't worry about the bottom values. The numbers we're not going to really talk about. It's something called an R value. It basically shows how correlated they are. So on either side, we have a perfect positive correlation. So this means our best fit line would perfectly predict any values that I would expect to get. Perfect negative correlation does the same thing in reverse. And you can see as we go in high positive correlation, my best fit line would be somewhere around there. Most of the lines are relatively close, but as I start to get further away, you'll notice these values become less and less close to my line. And then finally, right at this correlation, at no correlation, my line cannot predict. It is essentially random. So we can use, if we look at these scatter plots above, we can see which ones are more closely related to one another. Like for example, in my first example, the relationship is not great. You can see there's a bunch that are well above, there's a couple that are or a good chunk below, and it kind of follows this curved line. Same thing here, I'm having a number above, number below. This one is a much stronger relationship. You can see that they're relatively close in to this line. If I was to draw little distances, they're relatively close. I don't expect to find too many elsewhere. These ones here are slightly weaker. You can see, like, for example, this one and this one are pretty far away from my main line. And again, over here, I've got this one point over here and this one point up here that are a good chunk away from my best fit line. And if I was to play around with the line, I could maybe get them a little bit closer, but if I was to move the line so it was closer on this side, it's further away on the bottom one. So I have to give and take with this best fit line. Now, that is related to how closely connected these are. But there's so many factors when we think about real life. Like, if I think about this for a second, there's a reason why these lines are not perfectly connected, why the average daily temperature is connected to beach visitors. We can see that there is a relationship. Like when the temperature's low, like around 80, I'm not going to find 600 people at the beach, most likely. But it's not a perfect relationship. And the reason being is people's lives are incredibly complex, and that there's oftentimes so many more things than just one variable at play. So for example, if you can think for a second of a couple of things other than temperature that would affect whether or not someone's going to the beach. I'll give you a couple seconds and then I'll add a few of my own points. So other factors for people going to the beach. So a couple thoughts. Big one is weather. Now sure, temperature is a part of weather, but I might also look at the fact of whether or not it's sunny. Maybe this one was a rainy day and it just happened to be warm. That's going to reduce the number of people that go. Another thing might be time of year. It can be warm in the spring, but maybe if it's not during tourist season, there's no one really going, which would explain this same thing. Additionally, maybe it's a crappy day, but this one is on a holiday, which would mean that more people have the day off and could go to the beach. Even as simple as time of week or events. You can think of any number of things that could cause this to be affected by more than one variable. And when things are affected by more than one variable, it means that our line is not going to be a perfect fit to this one equation, and it's not going to be perfectly linear. The closer it is, we generally say that it's probably likely that the two are affecting each other, but it still isn't certain. So we've talked about correlation, we've talked about this positive and negative correlation, and then there's this idea of no correlation where things aren't related. So if you find a scatter plot, or if you make a scatter plot where the points are basically just put on at random, it's impossible for us to basically predict, or what we can say is that these two don't have that sort of relationship that I can predict or use one to be useful. So I cannot use my variable x to predict my variable y because it's everywhere. All right, this is another example of a low, like a positive correlation. We can easily see there is a trend going upwards, but you can see it's pretty weak. So we have radio advertising and we have sales. So again, this is a weak correlation. There is a correlation though. I can definitely see this sort of positive correlation that as radio advertising goes up, sales do increase. But there's all of these things down below here that are being or not really seem to be impacted. So this could, the way I can think about it is that there are other factors at play. So things like product quality, the quality of advertising, the audience. So if you're selling iPhone 12s, but the people who listen to the radio are not really tech savvy, like they don't buy phones that often, your advertising is misplaced, and putting more hours of advertising in is not going to get you the same results. Again, we can see that there are, or one of the things, the next thing I'll show you is that there's a very, very weak correlation. For this, I wouldn't expect anyone to be able to do this by hand, but computers can actually find if there is a correlation. So a perfectly flat line means that there's no correlation, but this one I can see is going up somewhat. So this is a very weak positive correlation, but essentially no correlation. And you can see that the points they basically look random, that as the temperature goes up, people are buying wraps basically irregardless of temperature. So there's a couple of examples of showing that even though things can be correlated, there's a different amount that they can be related to one another. And there's oftentimes other factors that are determining this. All right. I want to pause for a second because this comes up a lot, and this shows up in news articles. There's this idea of correlation and causation. So correlation, as we've talked about, is that there is a relationship or a pattern between two variables. Causation is the idea that variable A causes variable B. Now this is something to be cautious of because right away I'll say correlation does not equal causation. A great example would be I spoke with a toddler once, and they made this amazing leap of discovery. They were outside, so here's my toddler, not mine, but toddler, and it was a stormy day and it was raining. So they were outside splashing in the puddles, and they noticed, I'll draw it a little bit bigger. They noticed there was worms. So they noticed, and they put together the fact that over time they noticed when it was raining, there was worms. So they said, when it was raining, they saw more worms. So their conclusion was, worms come from the sky. Obvious, right? Now this is a problem of mixing up correlation and causation. We know, at least I hope we do, that worms don't in fact come from clouds. Worms live underground, and that when the soil gets flooded, they have a risk of drowning, so they need to come up so that they don't drown in the water-soaked earth. But there's a relationship here that you will see more worms when it rains. That much is undeniable. If you were to draw a scatter plot of rain amount and worm amount, you would definitely see, erase some of those. You would definitely see a positive relationship, that as rain increases, you're expecting to find more worms on the sidewalk. What this doesn't mean is that rain causes worms. The worms are always there. They are coming out for a relationship because of the rain, but not caused by the rain. So let me show you another example. So here is a very close relationship, a 66% correlation rate between number of people who drown by falling into a pool versus films Nicolas Cage has appeared in per year. So what they've done is the red line represents how many people have drowned versus how many films Nicolas Cage made in any one year. So we can see in 1999, Nicolas Cage made 2 films and roughly 110 people drowned. And we can see as we follow these lines, they seem to match up pretty closely. Like right here, we notice it goes way up and then way down. Weird. But here's the thing. They're not caused by one another. So there is a correlation. But there is no causation. So Nicolas Cage had no reason or like there was no connection between these two events. It was just a random coincidence that happened to line up. The thing is that these coincidences appear everywhere. If you've ever played around with some numbers or you've watched any videos of people playing around with numbers, you'll be able to find all these little connections. And if you've watched any sort of people making conspiracy theories, these are the kind of things that people look for, is that there is oftentimes, if you look within a large enough series of information, you'll be able to find these things that are connected. And news articles and other things will try to connect things that aren't really connected, but they appear to be because there's this correlation, or what appears to be a correlation. This is probably just a coincidence. There's really no way to connect these two. So one of the things I want you to keep in mind is just because there is a relationship doesn't mean that one is causing the other. It might be, but we would have to do more checks in order for this to be true. All right, next thing I want to talk about is this idea of an outlier. So here I have an XY plot. We have this correlated graph, and then I have this little dot right up here. So this is what's called an outlier. So an outlier is a data point that does not fit well with the trend. So a couple causes. Sometimes it is coincidence, or it might be a bad experiment, or what it might be is there is a third factor at play. So there's a third variable that we're not sure about, sort of this, you can think that there's a hidden variable. Something that's changing the value in a way that we're not expecting it to. You can actually see them in some of the points that I've brought up before. Like, if I talk about the average daily temperature in beach visitors, maybe on one of the days it was raining, and that caused the visitors to go way down. So this one, in this case, would be an outlier, because it's well away from our trend, and it doesn't help us at all. And in fact, it hurts our connection or our argument to say that these two are connected. So long as there's relatively few, it's not too bad, but the whole point of this is that oftentimes there's these other factors at play. All right, the very last thing I want to talk about is this idea of interpolation and extrapolation. So I'll define both first. So interpolation is using the trend line to estimate a value within your data. So inter means inside. So you're using a trend line to estimate a value within your data set. I'll show what both of these are. Extrapolation is using your trend line to estimate a value beyond or outside your data set. So Extra means outer, so like extra, think extraterrestrial for aliens or outside of Earth. Extrapolation is outside of our graph, we're making an estimation. So here I have a graph. I will draw a best fit trend line. So I will, and the goal when I draw these is I'm trying to keep as many above and below as possible. So I see that roughly if I go through here, I've got 2 above, 2 below, and then most of them are on the line. So like these 2 I would say are above. This one's a little bit above too, but for the most part, I'm kind of in the middle. So say this question asked me, or say they wanted to know the height at 15 months. And they'll probably say estimate. So what I want to do is I want to find 15 months here. I'm going to go up. And I'm going to go over and find the point where they cross. Dip down a little bit there. So what I see, this would be 70, so I'm going to guess somewhere in the middle, so I'd probably say approximately I'll say 75 centimeters. So this right here is interpolation. Because the point that I'm trying to get to, or the point that I'm trying to estimate, is within my data set. I have points on both sides of my estimate. And this is going to be important. Now, if I wanted to, if there's a second one, estimate height at, I'll go 30 months. I have to then go back to my line and I have to extend it outwards. Now, 30, this is 25, 30 is probably here. So I'm going to go up to around, whoops, bring it over just a bit, going roughly here. And then going over, I'm using a ruler for this one. I am going to estimate, oh, I got really close to 100, so I'll say approximately 100 centimeters. This one is called extrapolation. So keep it, I have to extend my graph. Now, of these two, I'll go over here. Interpolation is more accurate. And conversely, extrapolation is less accurate, and the further you go, the further you have to estimate beyond your data, the less accurate it is. So the key bit is, the reason why we can think about this is I have data on both sides. Chances are, especially with height, I'm not going to get a big jump. With height, if I grow to a certain height, I'm not going to degrow. So I'm not expecting the line to jump any higher than here. And I'm not going to shrink. So it's within that value. I might have a little spike or it might plateau a little bit, but I can reasonably be certain that I'm within a certain range. And most graphs, if you look at them, will, even if they kind of go up and down, you won't get a big spike or a big dip and then continue on. So because of that, we say that interpolation is more accurate. Extrapolation, however, because I have to go beyond my data set, the easiest way I can say this is things might change. And the example I've given is a perfect example of how things might change. We're looking at age versus height. If I look at age in years, this is a better example for height. So I notice at the start, there's this sort of line relationship here, and this is from roughly 0 to 10 years. And then I notice that the line kind of flattens out. And the reason is people stop growing. All of these dots are people at different ages, but we can see that the trend of growing doesn't continue indefinitely. Otherwise, if this was to be a pure linear relationship, I would expect the line to be going up and up and up, and someone who is 40 would be much taller than someone who is 20. So if I was to extrapolate, like say I only had this set of data here, and someone asked me age 40, how tall are they? You're going to go all the way up to, whoops. I'm going to go all the way up to here, and it's already off my graph, and I'm going to say something like 300 centimeters. They're going to be 3 meters tall, and by the time they're 80, they're going to be 5 meters tall. And that's not reasonable. So one of the things to be careful of is be careful of extrapolating too far. You can think of this as trying to predict future events. So for example, if you're trying to predict what's going to happen tomorrow, you can probably be pretty certain that it's going to be kind of like today. But if you're trying to predict what the world's going to be like in 50 years, then it's much harder to make that prediction. The same thing goes for a lot of these graphs. What might be a linear relationship could turn into a different linear relationship. Or in another case, we have heights of boys and girls. You can see that after a certain age, people tend to stop growing. Or in this case, maybe you have a relationship that isn't linear at all, but instead it's more of an exponential. So if you're only given a small chunk of data, maybe you make this connection that it's linear, and then if you continue it on, it quickly falls away from what's accurate. So here's a number of things that are kind of good to be aware of. They pop up in modern media a lot, where people will make estimations about, say, the stock market or something like that, and they'll talk about 10 years in the future, what they expect it to be like. And you have to treat those with a grain of salt, because at that point they're extrapolating. Whereas if they're looking at data within their values, if they get something on the far end, like say they know the heights of people between ages 5 and 10, it's much easier to guess the age of someone who's going to be 7 from that data set. A number of other things to be aware of, just in the real world while you're outside looking at information or watching the news, is this idea of outliers. Correlation does not equal causation, and just what it means for things to be related. That we can have relationships, but it does not mean that one thing is causing another, and that we can have things that are very strongly related and things that are very weakly related. And generally, the stronger the relationship, the more we can be certain that they actually are causal events, but even then we have to run more tests. So this should be enough to give you a rough idea of how to solve our assignment. The assignment is 3 questions. One of them is you're going to be plotting a graph, and then another one you're going to be answering questions around 2 already given points. That's all I have for you today. Take care, stay safe, have a good one. Bye.